is in the United States or in Europe. Okay. I thought with the topic which I want to talk about and so on, I settled perhaps maybe talk about MEMS and NEMS mass sensors, and this is the topic which I want to do. Okay. Before I do, for the young ones, I have two books, Perturbation Methods with Mathematica and one with Maple. You can download from my website for free, and essentially software, you might enter your equations and you get the answer with these. So that, and here is those. Okay, mass sensors, they have been essentially very popular and work quite a bit of extensive work being on the subject. Geometries, they have talked, you can take cantilevers, there might be microbeams, there might be nano wires, nanotubes, they would have comms, they would have arrays of them, and so on. You can have them clamped beams, and the clamped beams could be microbeams, nanotubes, nano wires. You can have plates and membranes, and you can have paddles, all sorts of configurations, geometric configurations. The classes of these sensors, they could be quantitative, where you have some environment, there is some gas, poison or otherwise in the environment, or some fluid, protein, you have some bacteria and so on. But in that case, you want to find exactly how much is there, the number, essentially. What is the mass which is there? And I'm calling those quantitative mass sensors. But then there is another class, which will be, I'm calling threshold sensors. You go to the physician, you have some problem with your throat, they will take a sample, take it to the lab. It takes 24, 48 hours to determine what type of bacteria which you have to give you the antibiotic. The question is, can you do that in the doctor's office? You take the sample and you put it somewhere in the doctor there with some device, and it will tell the doctor what type of bacteria which you have, so that they can prescribe, say, the medicine right away. And this, what I'm saying is, you look over those, what is the threshold? There's a quantity. We have bacteria everywhere, okay? All types of bacteria around us. But the ones which are critical, how much is critical for the doctor where you want to prescribe a medicine? Essentially, the answer, yes or no. But there's significant bacteria or significant virus or what? Yes or no. Okay, for the quantitative sensors, you might have static one, in which you do essentially the deflection. You take your device, you put whatever material which you have there, and then you look over the deflection and relate the deflection to the amount of the material which you are looking for. Or you might go to the dynamic mode, and in the dynamic mode, you look over something which you measure dynamically. And from that dynamic one, you can determine related to what the amount of which you have the mass. You look over shift in the frequencies. You have, for example, like a cantilever beam. You add to it a mass. It increases the mass increases that shifts the frequencies down, so that you might get what is the shift in frequency related to the mass of the material which you point. Maybe that might not be as sensitive and so on. You look over the resonant frequency. And if not, then you look over something which is horrible, bifurcation, and you look over the unsafe bifurcation, subcritical type bifurcation. Or you have some symmetries. You have a beam which is cylindrical. If you put in a symmetry, because you have the two frequencies in the two planes are the same, if you add asymmetry, then you break the symmetry. One frequency goes up, one frequency goes down. You look over the difference between those and related to that. Or you might use suggesting localization, because if you have two, essentially two systems close to each other, They have the same frequency, the same identical. You join them weakly. Now, if you add a mass on one of them, you break the symmetry. By breaking the symmetry, you shift the frequencies. But the major one is you are not looking for the shift in the frequency, but you are looking over the mode shapes, because you would have large difference in the mode shapes. The energy could be in one beam, say, for example, if two beams, or in the other one, so that you have a very large change for a very small mass which is added, and that will be essentially very attractive to do the mass sensing. The other thing which is very important, which I've seen, is we have seen in the macroscopic, in the shakers and the beams and the plates and so on, there are many nonlinear phenomena. And many of these are waiting for you young guys who are in here to see some of those in MEMS and NEMS devices, and perhaps exploit those types of devices and these phenomena for mass sensing. On the other hand, you have now what I'm calling the binary, the threshold, yes or no, which I mentioned there. You can have one of the major things which you say there is a sudden change in the system. And the sudden change could be with the pull-in instability, where you have the systems which are electrostatically, say, a beam or a plate, a membrane, and that will be the threshold which you want to use. And I'll explain some of that there. You take your system, you put a functional material to attract the whatever protein, whatever functional material which you are looking at, to attract it selectively. And then from there, determine in a threshold which is you have significant in it or not. With this one here, if we have it, then we don't need electronics. We don't need to measure frequencies. We don't need to have signal processing, because the answer is yes or no. And something simple of that, if I would say, being in Jordan there, they will take a scale, and you have, say, a watermelon which you want to buy. They put it, then they put all of those weights, but at the end, small thing, we put it. Does it come down or not? So essentially, similar. So that you put at the threshold where it is, a very small amount. If it put in, then essentially you have the pull-in. OK, so that no electronics. The advantages of those, they are robust and low cost. OK, now talking about the micro quantitative, I'm going to describe some of the work which we are doing with here Muhammad Yunus and his students. One of them is Adam Abu Shela, and they are, we do the theoretical, and they are going to be implementing it in the lab. OK. What I want to do as an example to show what can we do with perturbation. Since my background in perturbation, I need to push it in, OK? So that we have a cantilever. It could be beam, it could be nano wire, it could be nanotube, although here it's talking about the nano beam, nano wire, or the micro beam, because if it's the nanotube, we need to modify this electric one. So that you have essentially a beam equation, and since it's cantilever, the nonlinearity, whether it is elastic or the inertia, is small compared with this, so that the nonlinearity which you have is coming in from, this is the nonlinearity which coming in from the voltage. For a cantilever beam, the boundary conditions which you have in here, so that you have at the root, the displacement and the slope is 0. And at the other end, you will have the curvature and the shear force to be 0. We make it non-dimensional as usual. And then this is now the non-dimensionalized problem, which is in here. The first thing is we want to determine the static. We throw away the dynamic ones. And here, essentially, I have a mass. OK. I didn't mention that. Here is what the mass which we are adding, which we want to determine its magnitude over the length times the delta function, and we can put it at any location along the cantilever beam. By putting it non-dimensional, then the mass on whatever it is, alpha 1 here, and since the mass which we are looking for small, so that it will be now the perturbation there. But the first thing is, let's do the static problem. We throw away all of the dynamic terms, and then here will be the nonlinear equation for the static and its boundary conditions. Now, solving that, essentially, since it's for this problem in here, it's very easy to use Runge-Kutta or whatever to determine the solution, or sometimes people, they like to do Galerkin, what you do it. Oh. Having done that, now we will look over the dynamic part, so that you take the displacement here, the total one, is you have the static one, and you add the dynamic part, and we assume the dynamic part to be small, so that you linearize around it, and here will be now the result of the linearized, and it will have variable coefficients because the static problem, there's a static which depends on the space. The boundary conditions, they will be essentially the same, similar to what they have. Now, this is an eigenvalue problem, so that we want to look over the frequencies and the mode shapes, because we are going to use the shift in frequency as a measure of the mass, to do the mass. So that, as usual, we say now the displacement, you have a space eigenfunction, and then you have the frequency. So that from that, you can get an eigenvalue problem. So that here is the eigenvalue problem which we want to solve. Since alpha 1 is related to the ratio of the small mass which we are putting, I'm going to use it as a perturbation parameter, and to do a perturbation to determine the shift in frequency when alpha 1 is small. And so that essentially the eigenfunction is the one without the added mass, plus a small correction with the added from the perturbation. For the frequency is the original frequency, and this is the shift in the frequency. Substituting into those, you will get, as usual, two eigenvalue problems. You would have the unperturbed problem in here, which we solve, and then we have now the perturbed perturbation, the first order. Since this, the second problem, order problem, the homogeneous part is the same like the first one, then this will have a solution if and only if you have a solvability condition, which means that this right-hand side has to be orthogonal to the solution of the adjoint. It turned out for this cantilever one is self-adjoint, so that the answer now, I have the shift in frequency is minus the original frequency. Here is the eigenfunction evaluated at the location which I want, and then with that term. Now, from that, we can find the delta shift in frequency as related to the mass, which is delta mass, which is added there. And you see this expression, which is in here. If I use, say, this is the result for that. If I use a clamped beam, without boring you with the other results is the same, then we have the shift is essentially here, the mass, but then this is not self-adjoint, so that you have the original eigenfunction here is the adjoint of that divided by that term. If you use a membrane type behavior, then you have asymmetric modes and symmetric modes. For the asymmetric modes, you get, again, the delta frequency shift. Here is the mass, and here are the original frequency times those terms. If it's symmetric, then you can get that. So that if you look over those results, they are all of them similar to each other. You can make, for example, major statements about it. One is the sensitivity, delta omega over delta m, increases if the basic frequency of the system is high, increases. So that as you increase omega 0 here, omega mn or omega m0, which is the original one, you would expect to have a larger sensitivity, which means you would have big shift, or the shift in frequency increases as you put the mask. And if you want high resolution, then you want to go to systems which have their original frequencies very high, so that you need to go, instead of cantilever beam, to go to the clamp beam. Instead of going to clamp beam, maybe you want to go to a nanotube. It may be to want to go higher that, you go to nanowires. So that will give you the answer. The other one is the sensitivity is going to depend on the location where the mass is put. For example, for a cantilever beam, the maximum is going to be when you put it at the tip rather than other ones. You want to avoid this mass to go at a node, because if you have a node, then the phi 0 of that location is going to be 0, so that's no sensitivity. So those ones. Now, if you chose a system anyway, say nanowire, and you want the frequency, if you go to higher modes, you will get more sensitivity than if you get to the lower modes, because the higher modes, they have higher frequencies. So that these are the statements which I'm summarizing in here. The higher the natural frequency is, the higher the sensitivity is. For a given device, the higher the mode number is, the higher the sensitivity. And the other one is you have the sensitivity depends on the landing of the mass. And perhaps maybe you want your functional material to be at the tip rather at the node of the device. Okay, so that this is just summary. Quite a bit of work has been done by other people, by our groups on this subject. The next topic, which I want to go in, before I do that, these calculations just came in when I'm in here. Adam Abu Shala, who's working with Dr. Yunus in here, he has a cantilever beam with these dimensions to give you an idea about what we are talking about in magnitude. If you take the first mode for that cantilever beam, you have now the sensitivity is 0.4156 essentially hertz per picogram. Very small. If you go to the second mode, then instead it goes by a factor essentially of 5. If you go to the third mode, then the sensitivity doubles. So that the higher the mode, the more you have there. Now, if you go to a nanotube, on the other hand, we are talking now about different levels. We are talking about the sensitivity about 8, and that is per zeptogram, which is 10 to the 3 times more, or 10 to the 6. Okay? Again, you go to the second mode, instead of 8 now you have 48, a factor of 6. You go to the next one, then it will go even higher, because now the sensitivity is not per zeptogram, it is now the yoctogram, which is another. So that the higher the mode, you will get better. The system, the higher the basic frequency is, then you higher the sensitivity. Okay. Now, the second one is we have some nonlinearities, and the nonlinearities have to exploit nonlinearities. And one of the nonlinearities in these MEMS devices is the pull-in instability, which I'll describe. This work is done with Ethab Abdel-Rahman, and he had a PhD student Khater, Mahmoud Khater. And this work is applied for a patent and being licensed by a company in Canada to check for E. coli, because you have the vegetables and the fruits and so on with so many breaking of illnesses from the E. coli, and they want to separate the vegetables, whether they are safe or not safe. Okay. Okay. The basic system which we have the theory on, when we tried to put it implemented experimentally, is something different, which I'll do. But we started with a cantilever beam. You have a plate which is on it. There is a electrode under it for the driving. This plate, small plate, has a functional material to selectively, okay, absorb some of the ones which we want. It may be the material you want. E. coli, you're different. If you have ethanol, looking for that, different, for different materials. Okay. The main thing is we want to use the pull-in instability. And here is the curve, and many of you are working in the NEMS and NEMS. You have come across it. Here is the displacement. As the voltage increases, you would have stable, for example, this one here. It goes that somewhere. There's an unstable branch. Somewhere in here, there is a turning point. Beyond it, there is no solution. And so that essentially this mass is pulled down, or the plate pulled down. And it's called pull-in instability. The question is, what came to our mind is essentially what I said about the scales, which I put something, and it's on the verge of coming down. And by putting whatever amount, if it increases by this much, then it's going to pull in. And this is the idea which we want to do. Okay. You're talking now about with this pull-in, which is, you might use even another subcritical instability or some unsafe besides the pull-in to do the same thing. Okay. And this is what I explained that before. Okay. Here is the system. And I explained that it is a cantilever beam with the plate in here, so that I don't repeat myself that with the electrode. And when you have the functional material, and here it is. So that this is now the formulation, mathematical formulation. You will have the beam equation, linear, because it's cantilever. And the most important thing is the nonlinearity, which is coming in from the electrostatic boundary conditions. Since now the nonlinearity is at the tip, so that you will have the nonlinearity coming in from the boundary conditions, so that you have the bending is not zero, but related to the electrostatic force, and the shear force, again, it depends on how much you put electrostatic force there. Okay. For numbers which I want to give you for that, for anyone who is interested, these are the parameters for the plate and for the beam. Here is again, the curve for the deflection, but now the deflection at the plate, and the mid center of the plate versus the voltage. Again, beyond this VPI, which is the voltage pull-in. And by the way, if you don't know, VPI used to be the Virginia Polytechnic Institute and State University. Okay. So that this is now the pull-in voltage. Okay. So that what we want to do, first of all, to do a static sensitivity. Sensitivity, which is the delta W to go to pull-in. Let me go back to the curve. Okay. What we want to do is we want to come and set the voltage at some place in here, close to pull-in, so that there will be some displacement, delta W, and it will get it to pull-in. So that how much mass with the W to get us the sensitivity curve, which is if I have delta W over delta M as a function of voltage. And that will be sensitivity, and we see that's going to go to infinity as we come close to pull in. Okay? Now, what we want to do is establish a voltage close to pull in. It's on the verge of pulling in. And let me call that V0. Then that set up the first voltage. The output voltage, you need an increment, and how resolutely you can do it, and essentially it's 1 millivolt per volt. Then we find what is delta W, how much W is going to go to make it to go to pull in, which is from here. And then once we have that, then we go to the sensitivity curve, which is in here. We have delta SM from the sensitivity curve. We have delta W, and from that we can just get delta M. Give you some numbers for that. If the voltage is set at 8, then the threshold is 481 nanograms. If you come closer to pull in, then it goes to 331 down. Go to 8.2, 170. You can get here 8.2 something, 3, and then even you might get it way, way down, as I'll show you in the experiment. For the experiment, it turned out that that plate and so on is not good, okay, because it's twisting and so on. And so that they settled on having 2 anchors. And they have the 2 beams in here so that the plate, which is at the end of 2, to get them. The sensing material they used for the functional material in order to test for ethanol. And for ethanol, they have one which is this penny with 10% NiO, and the other material is the P25DMA. Do I know those? I don't know. Okay, but these are chemical compositions. Okay, from that, now we can get the sensitivity curve as a function of the voltage. They have the experimental setup, and the work is going to depend how close can you get to pull in and to make it stable, stay there, so that when you add the mass itself will trigger the pull in rather than triggered in from disturbances or that. So that the sensitivity is going to depend on the set-off voltage, how close you are. For this one here, the driving voltage in increments of 1 millivolt. The sensor have the beams, and here are the dimensions for those with the thickness and so on with the gap. And here is the setup. Okay? They have a canister where they open a valve so that they will get the mixture to come to this chamber. And from the chamber, they have the driving circuit, the laser, in order to determine when and not to see the pull in or not. Okay, and here are the details, if anyone is interested in the details of the circuit. And the minimum detectable concentration is going to depend on this delta V, how far you are from there. The type and the amount of the material which you have and the functional material. And what we found from their experiment at Waterloo, the detection limit, if you have the material, the system, but it is doped with the, this material, the penny with 10% NiO, to be 50 parts per million. On the other hand, if they use the other one, the P25DMA, it was, instead of 50, it became 5 parts per million. So that you see the sensitivity depending on the functional material. When delta V equals 1, to give it to you in numbers, the number is 165 picograms, so that they were able to detect a threshold of 165 picogram, which is very, very small. Now, the question is it stable, robust, what, and so on? It turned out to be very robust. All of the experiments were done in clean, not in clean room, outside. The probe station was not isolated from the ground, something like this. No precautions to protect the sensor against external disturbances, no. The stability against external disturbances, it was excellent. The key to it is highly damped. It's over-damped. And since it's over-damped, nothing is affecting it. But this is a bad thing which we are trying to solve, because when it comes down, it sticks. And we wanted to go back for another experiment. Okay? So that this is what we are working on right now. 2 minutes? 3 minutes, okay. 4 minutes, okay. Then it gives me time to talk about the dynamic part, okay. Now, for the dynamic part, we want to use something dynamic, okay. If you have something, a system, the same systems which we have, and if you look over, if you drive it to the nonlinear behavior, you would find now there is we put a static voltage, but then we put a dynamic part in here, okay? So that we are looking over the frequency response curves. For these systems in here, they are softening because the nonlinearity is coming from the electrostatic. And the electrostatic is softening because quadratic nonlinearity, and quadratic nonlinearity gives you softening type behavior. So that you have now 2 branches, this branch which is stable, but then you have this branch in here where you have stable, unstable, and this is a cyclic fold. What we want to do is to take something which is drastic, like the cyclic fold, use it for whatever we want to do for the threshold, okay? So that the idea now, suppose we put the system operating somewhere in here, the frequency, so that all of this the same, but now the frequency, we want to put it just to the left of the cyclic fold. If we add mass to the system, the cyclic fold will move to the left. Let me put a picture in it. Okay. Since the time is small. So that now, this is the curve which we had before. This is the cyclic fold. If we add a mass of 30 picograms, the cyclic fold is shifted by 29 hertz. So that now, if I operate the system at this location, frequency, if I add 30 picograms, it's going to be moving the cyclic fold this way here, so that what will happen to this system is going to be jumping to get out of it, which means now gives me the indication you increased your threshold with 30 picograms. And if you have, for the same thing, if you have 1 picogram only, the shift is only 3 hertz, so that the resolution of that, and there might be some problems now, issues with the stability, with the robustness, and so on, which is there. So that with this, I close and saying now, with this last part, we exploited some of the nonlinearities. And I hope some of the young fellows in here will work more on the things which we see in the macroscopic to discover it in these NEMS and MEMS, and perhaps exploit them for design for other things. And thank you very much.
Thank you very much, Ali. So the talk is open for discussion, questions, comments. Please, Maria.
Yes, Maria. Uh-huh.
The MEMS are modeled by mechanical engineers, and I have seen a lot of papers where the mechanical part is very well modeled, but the electrical part is basically, we just assume nonlinearity. I think you have terminals, you have a lot of complications which are practically important. So I would like to see your wisdom on that. Should we do a little bit more on this?
For the electrical.
For the electrical modeling.
Okay.
Because what we have,
when we started Marian, we started looking over the work of the electrical people. And the first paper which we wrote on the subject, and it was the stretching term. So that when the electrical engineers, they're modeled and with the electrical part, which we did in here, but when they did the stretching, they put a constant term. Okay, so that we started from there, so that we corrected what they have. So that essentially, we built on what the electrical engineers, and we added the structures correctly. Okay.
but I understand that you have two terminals. You have a distribution of charge. So basically, there is much more to it than
because you have now essentially what we do
Exactly.
is the parallel plate assumption. Now, the parallel plate assumption is an approximation. You would have the fringes and other ones, and some people, they look over the van der Waals forces and so on. But now, for our purposes, I did whatever we did. Now, you have a device, okay, and the device, you need to tune it. Okay. By tuning it, okay, it may be when I said 30 picograms, it may be it's not 30, it may be 25. But you tweak it, the system at the end, to take care of all of the corrections which we have.
The second question I have, you probably heard that many times. Your constitutive modeling for nanostructure didn't strike me is very different than for the classical mechanics. So where is the nano coming into the...
Essentially, most of the people, they have done experiments on the nanowires and the nanotubes, and compared with these, essentially, the rather than the quantum type behavior, okay, the physics is the continuum, and it turned out to be good enough. Okay.
To the effect of adding the mass.
The adding the mass, okay, if you are away from wherever the root, see, the root is going to affect the surface tension.
Yeah.
Okay, and some people, they worked on that area of the surface tension there. Now we are talking essentially more from the mass, the effect of the mass and shifting frequencies.
I understand, but you split in the quasi-static and in the dynamic part.
Okay.
And adding the mass would mean a Heaviside function in the mass in time, and then since the dynamic part is driven by the second time derivative of the static solution, you would have some dipole in the dynamic part. Possibly this is so small that you can...
Okay. The question is, what is the effect of the small mass on the static part, which we did not do, because it will have dual effect. Since it is a small mass, it's going to have essentially a static deflection and also a dynamic one. It turned out, up to now, the one which I did in here, it was only on the effect on the dynamic. But that would not be a difficult one in the perturbation to add it, and to have the static part, to have the added part in there. Yeah. Yes.
Okay. Ali, you investigated the nano and micromechanics aspect of this pull-in option. But it will be a fascinable application also in macroscopic structural control. Never exploited because it's too much nonlinear. Do you have any idea or example of application of the pull-in in big scale, larger structure?
I did not, but I think you might have something, and this is why I asked this question. And we'll be happy to work on that.